welcome you, and I would like to ask Manfred if he could also welcome us for this workshop. So Manfred, please.
It's a great pleasure for me to welcoming you all here in Germany, online from Germany, from a little village, Heckenbeck, 500 people, but nevertheless we broadcast into the world and we do research, online research and also offline. So Biljana and her colleague Igor Leschischen, they are visiting me the past week and the current week, and we are doing, data analysis, and I tell them how to analyze extremes. And so it's a great pleasure in these days of war and sadness also to do something positive, namely to work on science. And let us hope for the future. And I wish you a great success with the workshop. Biljana, she's just in the room down there, so perhaps I later have a look what she's doing. And I myself will also be teaching, I think on Wednesday, and I wish you a great success. Thanks.
Thank you, Manfred. For today, our first lecturer is Professor Rob Wilby from Loughborough University. Rob will tell us more about temporal scaling of subdaily extreme rainfall. Then we will have a short coffee break, and then a practical session, which will follow, and discussion time will follow this practical session. So without any further ado, please, Rob, the floor is yours.
Thank you, Biljana. Thank you, Manfred, and welcome everyone. I'm really so happy to be part of this cooperative venture, especially today. And it really gladdens my heart that we can work together on these things and share our ideas and hopefully move towards undertaking some collaborative research in this area. So I'm really excited to be meeting with you all this morning. Let me also just begin by thanking a couple of people. Minucha in the background has spent a fair amount of his weekend trying to make sure that the software will work. And I really appreciate you doing that at such short notice. And I'd also like to thank Manfred, who perhaps he doesn't even know it, but his gentle advice on some of the statistics has actually enabled me to make a big step forward in the development of this tool and to get around a roadblock that I'd been struggling with for a couple of years. So thank you, Manfred. You don't even realize that, how much help you've given me. Okay, so let's begin. Temporal scaling of subdaily extreme rainfall. This might sound like a really niche topic, but I think it's an important one, as I'll explain later. And it's also a topic that allows us to bring together many of the elements that we have been looking at over the last year or so now in terms of quality assuring data, statistical downscaling, checking for the homogeneity of data sets, and applying rigorous approaches to uncertainty in our analyses. So I'm hoping that you will see all of these elements coming together this morning. You might be wondering why at outset I'm showing us this slide of Kilimanjaro. Well, the case studies that I'm going to be referring to come from a big project involving UK and East African partners looking to develop methods of simulating future changes in extreme rainfall in East Africa. The High Crystal project. And I was fortunate enough to be one morning on a flight, and this was the view from the outside the aircraft of Kilimanjaro, which reminds me of this project as a whole, which I'll be drawing on. Biljana, shall I just try and share my slides from this end? Shall we just give that a go?
Yes, we have the permission for sharing slides.
Okay.
Yeah.
Okay,
it works.
Let's try that.
No. Yeah.
Might take just a few seconds to come through. Okay, can you see now?
Just the slide, not the presentation. Oh, yeah, now I can speak.
It's all good, is it?
Yeah,
okay.
yeah.
All right. That's the most nerve-wracking part of my day over then. Okay. So why should we care about extreme rainfall? Well, as I'm sure you all appreciate, flooding from heavy rainfall, pluvial flooding, is a hazard that affects most of our cities and is indeed is a global problem, a matter of concern. And in fact, just last week, I was caught in some very nasty flash floods in and around Manchester. Luckily, this is not my car, but I had to drive through a lot of very deep water to get to my meeting. So it makes you think when a major city such as Manchester, its drainage system is unable to cope with heavy rainfall. But as I said, this is an issue that confronts many cities worldwide. And so having a detailed understanding of the likely extreme rainfalls that our drainage systems might encounter is important. And also having an understanding of how that extreme rainfall might change in the future is also important. Unfortunately, globally, we have very little rainfall data that is, let's call it sub-daily resolution. So there's a fair amount of data globally that is daily rainfall. But if, for example, we want to know about sub-daily rainfall extremes at the hourly scale, this map shows you where the stations are. So that straight away you can see there's lots of blank areas on the map where there are no data at all. And even where you can see the data marked by the crosses, many of these data sets are 10 years or less in length. So globally, outside of North America, Europe, Australia, and Japan, and perhaps a little bit of Southeast Asia, we have very little rainfall data on which to inform these engineering standards and designs. We also know that looking into the future, global climate models tend to underestimate extreme rainfall. So in this figure, we can see at the top a map showing the observed annual maximum daily precipitation from the HADEX2 data set. And beneath it, we can see the average of the CMIP5 climate model runs representing the same period. So ideally, we would want to see the areas of very heavy rainfall shown in the red and the orange should be the same on these two maps. But you can see that in the climate model world, there's much less heavy rainfall than there is in the real world. And this is a well-known limitation of global climate models operating at these kinds of scale. Of course, significant advances have been made in recent years with regional climate models now operating at resolutions as fine as 4 kilometers in this case for the whole of Africa, or in some locations, for example, in parts of Europe at 1 or 1.5 degree, 1 or 1.5 kilometers resolution. And at this scale, we're able to simulate convective processes in the atmosphere, and through that provide much more realistic simulations of extreme rainfall. And these higher resolution regional climate models also tend to give us larger changes in extreme rainfall in a future climate. So if you just concentrate on the bottom two graphics in panel E and F, R25 is the projected change in 3-hourly maximum rainfall, mean 3-hourly precipitation intensity in the future at 25 kilometer resolution, compared with, on the right of it, a model operating at 4 kilometer resolution. And you can see much more darker green and blue areas in the right-hand graphic, showing that if you include convective processes at finer resolution or in a more realistically physically plausible way, then you get larger changes in projected rainfall in the future. But of course, despite these advances, the climate modeling is limited by the high computational demand. So these types of experiment tend to be run for about a decade or two at most. And so we still struggle a bit to capture the uncertainty in some of these projections, both in time and space. So this is what has brought me to now thinking about, okay, what simpler statistical methods might we use to represent extreme subdaily rainfall under the present climate and under changed climate conditions? And there are a number of ways we can do this. So there's a large group of researchers who like to use so-called weather generator techniques, which have different processes to simulate the arrival of storms, the number of storms, their clustering of storms, and then the intensity of rainfall. And I'm going to step around that big body of research today, and I'm going to concentrate on two alternative, even simpler statistical methods. And the first, summarized by this classic paper on the left by Menabdi et al., uses the fact that subdaily rainfall exhibits a fractal-like property. So the scaling of subdaily rainfall can be achieved by scaling from daily and multi-daily rainfall, and I'll explain that in more detail later. So that's one approach that uses essentially fractal scaling techniques. And the second approach, shown on the right, is where we don't actually scale the rainfall intensities, we scale the parameters of the statistical model itself. So if, for example, we're representing extreme rainfall using the Gumbel or GeV distribution, we can estimate the GeV parameters at different time durations shown along the horizontal axis, and we can show how those parameters vary with duration. So as the duration of the storm gets shorter, so the parameters in the GeV parameter space, the GeV parameters change as well. And that applies to both the location and the scale parameter, which you can see in the top two parameters, top two panels, and then the lower panel, there's a third parameter where there seems to be no temporal dependency. So in essence, we can relax this 3-parameter model to a 2-parameter model because only 2 of the parameters depend on time scaling. And I'm going to show you the extent to which these two simple techniques can actually replicate subdaily extreme rainfall just given daily rainfall information. So using more readily available data, we can get pretty good estimates of subdaily rainfall extremes. And as I mentioned at the outset, I'm going to be drawing on the High Crystal project because this project captures the main elements that I've been sharing with you throughout the EXtremeClimTwin project. And there are elements here around quality assuring the data, about identifying suitable predictor variables for statistical downscaling, building a downscaling model and testing it against historic series. And then today we'll be taking the additional step of temporal scaling data, in this case using a 2-parameter Gumbel model, and then finally seeing how well this temporal scaling performs within the virtual world of a regional climate model. So which of these scaling techniques seems to work well for the present and also within the the changed climate conditions that we might imagine in the future. And here are the two test cities, Kampala and Kisumu. Both of them lie within the Lake Victoria basin, and both of them, as you can see from the previous graphic, experience recurrent flooding episodes in built up areas. So this provides a really powerful case study, because we already know there are significant human impacts from flooding and damage to property. We also know that within the Lake Victoria Basin, from those projections I showed you earlier, we expect extreme rainfall to increase in the future. And we also know that we have relatively little data with which to build our models. So it has all the ingredients coming together to test the robustness of this modeling approach. And this is a workflow diagram taken from a paper that has recently been submitted covering this high crystal project. And the four elements that exist within the workflow are essentially testing the quality of the data, building a spatial or statistical downscaling model, using the daily information from that downscaling model to build a temporal downscaling model, and then evaluating the performance of this model against historic information where it exists, or sometimes we have to refer to published tables of intensity, duration, frequency data for heavy rainfall, which are more readily available. So I think one of the messages from today is that sometimes we have to be quite creative about where we can find the data to test these models in a data scarce or data sparse situation. And that will certainly, I think, come across in the practical exercise after the break. So let's just step through and illustrate these 5 activities. And again, I just want to really repeat what I said earlier, that here are hopefully are elements that you've heard me speak about before in various EXtremeClimTwin sessions. So we've done sessions on how to quality assure data by, for example, simple checks around, are there any day of week biases in the data? So we can look at how does the mean wet day, the frequency of wet days, or the frequency of very heavy wet days vary by day of week as a simple test of whether or not, in particular, manual observations have been aggregated at the weekend. And for these 2 sites, we're reasonably confident that there's no weekend bias, although if you look for Kisumu on the bottom right-hand panel, you can see a large number of heavy rainfalls on the weekend. Excuse me, I'm just going to put the light back on, which turns off when I'm not moving around enough. There we go. So when we see that sort of peak around the weekend, that can signal that there's been some aggregation of data across the weekend. And indeed, for this record from Kisumu, which was provided by the National Meteorological Department, we have some concerns about the underlying quality of some of the extreme values in this data set. So we need to keep that in the back of our mind when we come to the point of testing the temporal scaling models. I've mentioned before, another nice test is the so-called 5-10 bias, the fact that people all over the world prefer numbers that end in a 0 or a half unit. And you can see that for Kampala and Kisumu, there are notable spikes above the expected frequency of wet day amounts around whole numbers. So people like the whole number 4 and 5 better than they like the number 4.1 or 5.1. So that shows some number bias, and it's a very, very common phenomenon that we see. What we're really interested in is any number bias at the larger events above 50 millimeters, and we checked that and found that there was no discernible number bias for the very heavy rainfall events. So in our mind, the data set passed this particular test. Okay, so the second activity is then to think about what are the atmospheric conditions that tend to associate with very heavy rainfall and very severe flooding in these two catchments. And we've done this by comparing the historic rainfall data against media stories reporting flooding. So we've essentially used the dates of the media records of flooding to pull out the information about the rainfall and the atmospheric conditions on those days. And we did this over a 16-year period using newspaper records and some social media information. And as well as helping us to think about what were the atmospheric conditions leading to flooding on these particular days, this information can also tell us what is the size of a rainfall event that tends to cause problems, causes damage to property, or in the worst case, loss of life, which does sadly occur in these situations. And from these media records, we've established that if there's about 20 millimeters of rainfall over either of these cities, this can cause localized flooding. And it provides us with a simple metric for analyzing how the frequency of those damaging events have changed through time and how frequently they might become in the future. This information can also be used to help us decide which predictor variables to use in our statistical downscaling model. So what I've done here in this graphic is to compare the value of selected predictor variables on days before a flood, during the flood, or on all other days, so with no flooding episode. So we're particularly interested in those variables where there's a big difference between days with flooding and all other days. And so, for example, if you look at the top graph, you can see there are differences between the green and the red and the blue bars in some of these humidity variables. R500 is the relative humidity at 500 hectopascals. R850 is at 850 hectopascals, and then PWTR stands for precipitable water within the atmosphere. So we can use this information to guide the calibration of our statistical downscaling model so that it is particularly tuned to simulate extreme rainfall events and flooding. And as far as I'm aware, this is the first time anyone's actually tried to calibrate a statistical downscaling model in this way. This is a novel approach for building a statistical downscaling model with a specific use in mind, which in this case is to simulate extreme rainfall and local flooding. And you can see that whether we're looking at the predictors for heavy rainfall or the occurrence of flooding in the media, we can see a very similar pattern in the predictor variables that are selected. And this helps us to build a model, as I said, that is tuned to downscale those unique or those relatively rare conditions that generate extreme rainfall in these two cities. Then we come to the statistical downscaling step, which is to build the model using the available daily rainfall records. And for many of you, this tool will be familiar, or an earlier variant of it will be familiar. And and after the break, we'll be working with the latest version of the statistical downscaling model, which includes a new capability to model sub-daily rainfall extremes. And here again, for both cities, historically, we can see that the model does a pretty good job at simulating the seasonal variation in the number of wet days, the monthly rainfall totals, and the maximum 1 day and 2 day rainfall totals. So this is based on, you know, standard tests that we have gone through in previous workshops to see how well the downscaling model shown in the red compares with the historic data. So when we look at graphs like this, we're reasonably happy that the downscaling model is simulating the daily rainfall series pretty well. We can also go back in time, and I just show this graphic to remind participants that this downscaling can be used to rebuild or reconstruct rainfall records that might not exist. So because the predictor variables are available from 1948, we can calibrate our model. For example, for Kampala on the top left, we can calibrate the model, and then we can run the simulation back in time to build a much longer rainfall series to understand whether or not there are any trends or changes in variability in extremes through time. And we did the same for Kisumu on the right-hand side. And that's, again, a very powerful aspect of the downscaling tool, is that you might only have a few years of rainfall data on which to calibrate your model, but this tool can quite robustly rebuild, reconstruct records that may not exist or may be partial. We can also show how the downscaling model captures extreme value distributions, and there are 3 rows here denoting 3 different sets of predictive variables used in the statistical downscaling model. So the top row shows if we downscale extremes using just precipitation from the climate model as the downscaling predictor variable. And if we compare that with the bottom line, this is the predictor variable set based on the variables identified from the flood media stories. So if we just tune the model using the variables from that, and you can see that from the mean absolute error in the statistics, that actually downscaling from rainfall alone overall provides a very robust model. And so this is something I think we've talked about before. Is this legitimate to do in statistical downscaling? And I think it's fair to say scientists have different views on this. But here we can see that a simple model using just large-scale rainfall from the climate model as input to the statistical downscaling gives us quite robust estimates of the extreme value distribution at both sites. You can see for Kisumu, the black line, which is observed, tends to lie at the margins of what the downscaling model predicts in all variants. Again, I'm not particularly concerned about that because I know that there are some suspect values within this series. So we have to be treating this information with, as we say, a pinch of salt. Now then, so the topic of today, which is the temporal scaling, is once we've got our daily rainfall series downscaled, the next step is to disaggregate those daily data into sub-daily extremes. And as I indicated at the outset, we've got these 2 approaches. One, we're using a fractal technique, which we can see here, very clear evidence of scaling of the rainfall intensity with duration when we plot both on a log-log graphic like this. And what we're looking at here is essentially 4 or 5 years of 15-minute rainfall data from an automatic weather station that we installed in Kampala. And what's very interesting from this is that we see that the fractal scaling, I think, holds up to about a 1 hour duration. And then you can see that at shorter durations, the expected intensity is less than the fractal estimate. It falls away, the dots fall beneath the line. And I think this is a useful example to illustrate that we may have multi-fractal or multi-scaling going on within a data set. And that here we can see the scaling relationship is robust up to about 1 hour duration, but I would be reluctant to use this scaling relationship to estimate beneath 1 hour, say for 30-minute or 15-minute resolutions. And the technique developed by Manabe is the method of moments. And this is quite a complicated step-by-step procedure whereby annual maximum series of rainfall intensities at 1 to 2 to 3, 4, and through to 15 days duration are raised to a power 0.5 or raised to a power 1, raised to a power 1.5. And this is what I was saying. Thank you to Manfred for helping me understand what was going on with this technique. And for those of you who really want to drill into the detail of how this technique works, I've produced a little Excel spreadsheet that step by step takes you through this procedure using the data for Novi, and I'm happy to put that up on the site to share with folk afterwards. But take my word for it that by scaling from 1 to 15 days, we can see for Kampala and Kisumu, using this method of moments, we can essentially derive this parameter on the right-hand side, which we can think of some sort of fractal parameter that represents the scaling within the data set across different durations. So minus 0.8 for Kampala, minus 0.68 for Kisumu. And I highlight the difference here because this is something I'd like us to talk about later today, the extent to which variations in latitude and longitude and elevation, distance from coast, determine this scaling parameter. And I think this may be an interesting research opportunity for those of us working together within EXtremeClimTwin. But you can see how nicely the scaling parameter fits onto the data here. And as I say, I've tested this using 2 or 3 sites across Serbia, and it works just as well in Serbia as it does in East Africa. The second method that I mentioned is the method of parameters. And this is where we scale not the rainfall intensities, but we scale the parameters of our chosen distribution. And here I'm showing how the parameters of the Gumbel distribution, so the location and the scale parameters, how they vary with the duration of the rain event. And once again, we can see that there's a nice linear relationship through time when we produce a log-log relationship. So with that relationship based on daily data, we can estimate what the Gumbel parameters might be for sub-daily durations. And that's how we use this information within the new version of the statistical downscaling model. And here's the truth of the matter. How well does this work? We've compared the various methods using the small amounts of historic data available for Kampala on the left and Kisumu on the right. And what we're looking at here is the extent to which different types of temporal scaling method can simulate the 1 hour extreme rainfall or the 3 hour extreme rainfall. And bear in mind that all of these estimates shown in the colored bars compared with the purple bar and the dark blue bars, which we might think of as the truth, all the other colored bars are estimates that have been based on daily data. So we have no sub-daily information. We're just using the daily data to find the scaling relationship to estimate a 1 hour or 3 hour extreme. And you can see that some of these model variants work very well indeed. Where you see a little letter P at the end of the descriptor, that's where we've used a method of parameter scaling. Where you see a little m, for example, SGSM M, that's where we've used the method of moments for the scaling. And overall, we can see that the parameter scaling method seems to work better than the method of moments at these two sites. It tends to give a lower error when compared against the observed data. And this, to me, was actually a surprising result because when we look at the literature, the vast majority of studies so far have used the method of moments for estimating subdaily rainfall. Very, very few people have used this parameter scaling technique, which here I was pleased to see actually works better than the more widespread technique. And in this rather complicated, nasty table, where I've got lots of different experiments using historic data and then using output from regional climate models and seeing how well we can temporally scale using regional climate model information instead of large-scale atmospheric circulation data from observations. And I've highlighted in the red boxes the model variants that work best for using different types of input information, whether it's observations, whether it's from reanalysis, whether it's from the P25 regional climate model, which is the coarse resolution one, or CP4, which is the fine resolution convective permitting regional climate model. And then in some cases, we've got hybrid models where we've used the statistical downscaling to add resolution and bias correct the regional climate model information. So lots of model variants here in terms of the input information. But the key message I'd like you to take away looking at the red boxes is that in all cases, the model variant that uses the parameter scaling produces the smallest error when compared with the observed or the best proxy for observed data. And finally, we go to task 5, activity 5, where we're looking to see how well this model works in a changed climate scenario. So what we did here was it's a rather unconventional experiment. We actually used the regional climate model information with the temporal scaling technique to estimate the hourly rainfall intensity in the regional climate model. And then we can compare it with what the regional climate model actually saw as the estimated rainfall. So we're using the regional climate model experiment to test the robustness of the scaling technique. And what we can see here in the orange and the blue is that similar intensity duration plot to the one that I showed you earlier. But the difference here is that the blue line denotes the scaling under the present climate, and the orange line denotes the scaling under the future climate. And the take-home message from this is that the pattern of the relationship is roughly the same, but in the future, the whole scale has been lifted upwards as we expect a warmer atmosphere to hold more moisture, and in such a way to be able to generate much larger rainfall extremes. And again, within those changed climate experiments, we find that the parameter scaling technique produces, in some cases, much smaller error estimates when compared with what the regional climate model itself thinks should be the 1 hourly rainfall. So we're using the daily information from the regional climate model to estimate the 1 hour rainfall intensity using the statistical scaling technique. Now, this is again a method that relatively few people have used. I think it was Stephen Charles from CSIRO who first sort of came up with this clever idea of testing the robustness of downscaling techniques within the modeled world of a regional climate simulation. The difference between these columns, by the way, is the number of days over which we create the temporal scaling relationship. So we might try to estimate the subdaily rainfall using 1 and 2 day annual maximum series. That would be the DU2 column. Or we might develop the scaling over 1, 2, 3, and 4 days. So we're using a longer memory to create that subdaily scaling. And this upper bound duration parameter is an important one because it varies around the world depending on the local climate regime. And again, this is something we'll come back to later. There's evidence across Europe that this value could be as large as 10 days. You need 10 days of daily data extremes to create the temporal scaling relationship. Whereas in East Africa, it seems that somewhere between 2 or 4 days gives you the most robust model. So nearly finished now, just some closing remarks, and then I'm happy to take any questions. Obviously, this is very early work. It's just based on, at this stage, 2 cities in East Africa. And what we've learned from this pilot experiment is that contrary to the theory, which assumes a single scaling relationship, observed data actually tends to have a multi-scaling relationship. So we do see these breakpoints in the scaling relationship, like I illustrated for the automatic weather station data in Kampala. We also noticed that on a rain day in East Africa, it's not actually raining for many hours in the day. So we might have a 1 day rainfall total, let's say, which is 50 millimeters. But in reality, that 50 millimeters didn't fall throughout the 24 hours at a uniform rate. It actually occurred in a relatively small period of time when much higher intensities occurred because the duration with actual rainfall is shorter than the day. So again, I think this is something that has been relatively neglected by the scientific community so far when estimating subdaily rainfall extremes, because the assumption is that the daily total somehow gives us a uniform intensity and all hours are raining. But in most situations, a rain day seldom has all hours delivering rainfall. And that's an important adjustment that we need to make to the models to get a more realistic estimate of the intensities. We also have to test for the records that we're building our models on are homogeneous and that we have confidence in the extremes. Whilst I'm quite confident with some of the data I've used, as I've mentioned already, there are some outliers within the data which are suspicious. And indeed, we can use the media records to triangulate, to try and test whether or not the value is realistic. For example, if you see a one-day rainfall total of 100 millimeters, but there's no record of flooding or heavy rainfall in the local media, the chances are that that is a data entry error. It might be a 10.0 rather than 100, for example. We've also made the assumption that the Gumbel distribution is the one to scale. Others have used GEV. I'm a great fan of keeping life simple and going with the simplest possible model that gives us the closest to best results. I actually like Gumbel because it only involves working with 2 parameters. As I came towards the end here, I was signaling that we need to think about the upper bound duration over which we do the temporal scaling, 1, 2, 3, 4, or even longer durations to get the short duration estimates. And we can't assume that that's the same everywhere because it does depend on the climate regime. In some parts of the world where the very heaviest rainfalls are delivered by multi-day events, that may provide useful information. And finally, I think the media analysis does provide us with a really simple but nice way of identifying the rainfall thresholds that matter to people. You know, what amount of rainfall delivers an impact that is sufficiently severe to be newsworthy. And I think that's where we can bring these 2 worlds together of media analysis and meteorological data analysis into new territory. And it's an area that hasn't really been explored. And there are some emerging studies that are using Twitter and other social media to identify these kinds of thresholds or to develop proxies for rainfall where the data do not exist. And then finally, some concluding remarks. What were the insights that we got from the High Crystal project? Firstly, as I've said, the media reports can give us really nice diagnostics for looking at how impactful events have changed through time or in space. So how often do we get 20 millimeters of rainfall in Kampala historically? How often might this event occur in the future? What types of what are the implications for urban drainage design if we want to manage these types of event? We found smaller errors in this temporal scaling using the parameter method than the more widely adopted method of moments, which was a surprise to us. But again, I think we need to test that more extensively to see whether that's a global truth or not. Thirdly, as I've shown, it doesn't rain all of the time during a wet day. And so we need to pay more attention to rainfall intermittency within these models. And fourthly, we showed that the convection permitting finer scale climate model delivered credible scaling relationships. So we see the same statistical scaling relationships in observations, and we see the similar scaling relationships within regional climate models. So that's telling me that at the statistical level, these models are delivering equivalent fractal properties as we see in the real world, which I think is a really interesting result in itself. So in summary, I think there are some exciting opportunities for future research here. And I think this is something I would really like to progress with the EXtremeClimTwin team, going beyond this workshop, looking at how we can use these insights to develop the downscaling techniques and perhaps even show the extent to which these combinations of dynamical and statistical downscaling methods can give us really nice and accurate estimates of extreme rainfall at sub-daily levels, even where we only have daily data. And that's the crucial thing. For most parts of the world, daily data are all that we have available. So this underlines the need for these simple temporal scaling techniques. And with that, Juliana, I'd like to hand it back to you and see if there's any questions. I know that was a lot to share with people first thing on a Monday morning, but I hope it triggered some interest in some of the opportunities that could emerge from these techniques. Okay.
Yes, thank you, Rob, very much. This was a nice presentation, and actually it should give us some ideas. What should we do next, and what can we do and make new research into this Western Balkan part, which actually lacks in this kind of data. The problem is actually that we in Serbia, I think we have sub-daily data measured by the meteorological services, but they don't share the data, so it can be pretty tough to get you know, the results compared and see if our model works fine. But we will see. We'll try to reach out and see if they are willing to collaborate with us.
Well, I think I mean, you kindly shared some automatic weather station data with me, and what struck me was, I mean, it was some very rich information there, but the formatting of the data is sometimes quite hard to interpret as well, and there may be that there are opportunities here for a wider conversation about how do we, you know, capture sub-hourly rainfall information and store it in ways that are you know, useful for people. Do we time the tips of the bucket? Do we give an accumulation every minute or every 15 minutes? What's the most useful format? So I think that there's everywhere there's always a need for those kinds of conversation. Yeah.
The data actually that I shared with you is a part of another project that was going on at our department. They kindly share the data with us, but they only have 1 year of the data because they put up the sensors around Novi Sad, and that's the only data that we have at the moment. Yeah.
Well, that was very kind of them to share the data with us, and I will be referring to this information later, because it nicely illustrates this issue of intermittency. If you look at that 1 year of data for the event with the largest total, or the most intense rainfall, you can just see how few hours during that particular day there was actual rainfall.
Yeah. I'm really looking forward to see that. So does anybody have any questions, suggestion, idea? Please share. Manfred, maybe? No. Nothing. I'm really looking forward to see how it can be done for Novi Sad, for example, because here in Novi Sad we actually have the problems with those floods during the storms and everything. Those drainages get clogged, and a similar situation like you showed on the first slide in Manchester. Similar situations happen in Novi Sad. I'm sure they happen in Belgrade and other cities in Serbia. So this can be really useful information.
Yeah, in fact, to tempt people back after the break, I am using worked examples for Novi Sad and Beograd. So I'm using your actual data with information to hopefully show how well this temporal scaling works.
Maybe I may add a comment. I think it's very helpful if we combine the rainfall measurements with the flood measurements, or more generally the runoff or water stage measurements in a river, because a river integrates over an area, and that may give us a handle on, well, to assess the spatial rainfall amounts with what arrives in the river. Maybe we have then to discuss about the time scales, because it takes a certain while, but I think such comparisons, rainfall and runoff we can learn quite a lot of them.
Yeah.
Maybe it's feasible for our project.
Yeah, thank you, Manfred. In fact, the second case study I'm going to show for Beograd, that's exactly what the researchers did. They used the catchment area as this integrator. They recognized there's the time to peak, so there's a lag in here as well, and they're working out, doing the calculations to figure out what the drainage system needs to be able to cope with over different durations and for different return periods. So exactly as you suggested.
Well, do you have an idea about in the past we had these the different cyclonic pathways, so they come from the Atlantic, then they move over France or so, and travel to the Central and Eastern Europe. And for example, the 2002 flood in Germany, which was a devastating event, it was caused by a so-called 5B weather situation, where a cyclonic, a low pressure system travels till over the Gulf of Genova, and then the Adriatic Sea, and then it moves northward, and then at the Erzgebirge mountains it stops and it elevates, and then we have orographic rainfall, and this low pressure system remains stable there for 10 days or so, and it sucked the moist air from the Adriatic, and this brought our floods. And I could think that at other stations in the in the Balkans and Serbia, 5B could as well be relevant. So maybe not in this project, but maybe in the future we can have a look whether it's possible to kind of predict such synoptic weather patterns and the cyclonic pathways, whether or not they can be shown to have an influence on Serbian floods.
Yeah, I mean, that also fits very nicely, Manfred, with the example I was showing where we use the media analysis, the reports of severe flooding to identify the dates of these events. So you can link to the media and the impacts, but you can do exactly as you said as well, which is to take information about the atmospheric circulation on those days to stratify the data and say what was peculiar, what was unique about the atmospheric circulation or the moisture content or the pathway of the cyclonic systems, or the stagnation, the persistence of the systems as well that delivered these extremes. And you can do that analysis.
And whether that will be worse or higher risk in the future. And maybe the Cicero guys will show us data which we could analyze and put in